Okay, we're going to continue with lecture 3 today. It's again early in the morning. We did not get it filmed last night. The second part of lecture 3 is about canopies. Again, our small children are asleep, so I'm going to be talking somewhat quietly. Dave, when he appears, will likely not, because he's got the loudest voice in the world. But we're going to be trying to be mindful of the kids, and one of us might disappear for a while to deal with small children as they wake up. You're starting to see a pattern now on how we run these lectures, and some of the information, not a lot, is starting to be repeated. So we might go a little bit faster on some of these, and I really want to get to some of the anecdotal stories, because really that's, I think, for a master's elective like this, that's where the true learning is, hearing what happened. You know, you can read all of these and study all of these, but it's really the hearing a story about it that's going to lock it in your mind, I think. That said, I have to test you and I have to do all the stuff to kind of meet the requirements that accreditation sets out for this to be a viable course. But what I really want to get to is kind of the stories Dave and I have from working on these. So at first I thought, oh, I'm going to have a hard time finding enough canopies. In the end, I had to cut out half of the full example ones and switch them just into pictures because I just had too many canopy projects. Often when we talk about a canopy, we assume that it is stuck and attached to the building. That doesn't have to be the case. It's usually anything that is providing a shade structure or a snow, like a protection from the elements that is both exposed to the weather, top and bottom. I don't mean snow can fly up, but I do mean that there's usually nothing enclosing it. There's no walls. So it's a roof with no walls is often what we're defining as our canopy here. And it doesn't even have to be a fully enclosed roof. It could be the element we're trying to protect from could be sun. It still gathers snow and it still gathers wind, but its purpose could be protecting from the sun. So strength. Canopy loads are probably one of the most similar to a building conceptually. We have our superimposed dead loads and we have our self-weight dead loads. Live loads, some canopies are accessible. If they are an overhang over a door or something over a door. Oh, I should have been, when Dave and I got married, we eloped to Whitehorse. And Dave rented us the best hotel room money could buy in the town of Whitehorse. It was amazing. It was wonderful. Being there was so spectacular. And he got the one with the private patio. And it was a huge patio from the images, and it was fantastic. When we got there, our room was over the front door, and the patio was actually the roof of the canopy, so you were very exposed, and so private just meant that no one could access it but us. We didn't spend a lot of time out there, especially because of the big blue glowing light that shone both forwards and backwards onto the canopy, but the thought was lovely. People, you have, if it is accessible. If it's not accessible, don't worry about it. You don't have to design for a live load. Often, sometimes during construction, you might want to think about somebody being up there assembling it. So sometimes, depending on the project and the size of it, if I know they're going to have to get up there, or possibly if they're going to build it in parts and hoist it in, normally that would all be under construction loads. But a lot of these are, so if it is people accessible, 1.9 or 4.8 kPa, depending on whether it's a residence or kind of a public structure. But if we do other small point loads, it might be because of erection sequencing or somebody getting up there during construction. Like I was saying, that would often be the scope of the contractor. But these are such small scale projects that might get missed. The contractor might not exist. It might be just the owner hiring a fabricator. So that kind of critical step might not be there. So often, if I have access to the fabricator or during the process, I'll ask that question, and we might build that in as one of the load cases. It often doesn't govern, but it's good to know that it was checked, so there's no surprises kind of going into building it. Often these might be used as a green roof. Green roofs, there's a lot of products out there that can be low weight, so this is really dependent on the product. Often, most of them, kind of the lightweight ones are around 2.0 kPa for saturated soil, but those are the really light ones, like kind of you buy a tray and you place them up on the roof. The City of Toronto has a really rigorous green roof report. The two things they kind of really obsess with right off the bat on a permit application for anything are wind uplift and green roof. They say they need a report, but often the report can literally be embedded in the structural contract documents, where you have a wind uplift diagram or notes about your green roof on your diagram. But often they make the engineer and the architect sign a special report or a special file, PDF, saying that they've considered all the things for the green roof. If you're doing something really fancy or sculpted, you could have big mounds of soil, and the big weight there is when it's wet, because when the rain falls, it doesn't just run right out, it absorbs that, and it can get quite saturated and be quite heavy. So you have to think about the saturated soil, not just the weighted soil. Wind for the canopies can get quite interesting. Our code isn't fantastic in Canada because you can imagine most of the wind loads we had for low structures combined CPCG for a roof. You guys didn't really see this diagram before because we only focused on the building as a whole, but I had said that there was like numerous things we needed to think about when designing for wind for a building. And one of them is a very specific diagram for wind uplift. So wind kind of suctioning off the roof. We still have to worry about wind downward, and that's become even more important in our new load combinations. And I think I've mentioned this a few times, that the National Building Code in 2015 changed the combination loads, where we now have our dead load, our main load, and instead of 0.5 or 0.4 for wind, we have 1 for snow or live as a companion. And it's still only 0.4 as a companion load for wind, but if wind is the principal load of 1.4 and we have wind, and we have snow, the snow needs to be 1. So that can really increase the amount of load our elements are seeing. Now a canopy, when wind is blowing on it, we have a downward and a suction force downward, or we have a suction force upward and a wind force underneath pushing upwards. So our code deals with this chart. So this is our roof wind load graph for determining CPCG. You remember IW is our wind importance factor. Q is our climatic data that we look up in the building code. CE is our exposure factor that increases with height as we go up. And CPCG, CP and CG can be separated depending on what type of calculation we're doing, but our building code often lumps them together for certain things. We've seen examples where they don't. So sometimes you need to think about what that gust factor, CG, is. But for these, they've combined them into one factor for us and called it the CPCG factor. So this is our CPCG factor graph. And you can see that there are positive and negative values. And we need to worry about, so if you read this instruction down here, it talks about the ones with the O being an overhang. That means that they're exposed from both above and underneath to wind. This kind of implies that there's walls around it, that's a small section. It's a good place to look up these values. It can be a bit conservative. I don't mind this for small scale elements where snow is usually the governing load anyway, because we find that it doesn't have that big of an impact on the overall design. If we have something slightly more rigorous or built in a place that is very wind governed, the Australian code has a really good open structures kind of wind clause. That's where you go, right? That's where I go. Or have you changed where you go for your...
Yeah, ASC7. Oh,
for
yeah,
open
structures.
For open structures, yeah.
Yeah.
So we used to go to the Australian code. I do most of my canopy work in Toronto, and snow just far and above, and you're going to see why, governs. Dave's been doing a lot of fabric structure canopies in kind of southern or equatorial regions, and wind so highly governs that it becomes a really refined process. But for me, for most of my stuff, using what's directly in our code is totally fine. So this is where knowing your codes can be really important, and when it's okay to deviate from our code. This was intended for things like small canopies. I'll apply it to kind of a small canopy structure, independent from a building as well. But if it is really heavily governing the design, it might be worth exploring alternates. And the building code does accept this. We've been through the process several times. So we have to worry about applying this wind load downward. So that would be these positive values, and upwards, which is these negative values. We also have to worry about a drag force or a projection of wind on the side of these. They have no walls, which is normally what governed our wind design, but we do still have structural elements with some sort of surface area that wind can blow on from the two sides, or even columns. Sometimes that seems a little bit low for a wind force. Columns have a very specific spot in the code because they are a round element, and they create turbulence. So they have, the same way we have the wind wall diagrams for our guards, there is one for things like standalone columns and cables. So we can access what the wind load is on those surfaces. And then if I find the projection on the side of my canopy seems a little bit low, I might look at taking a drag force as a percentage of what the up and down force is. Do you follow that? Do you do that too?
Yeah, in fact, ASC 7, which is the American code, has a specific provision for that. Something like 1% of the
depending on
projected wind load.
Yeah, I use about 2% just to be conservative, because that isn't, I'm not usually applying that with snow load, because snow load is a gravity load, and I'm applying these independently.
And of course I'm doing it on fabric structures, which are very smooth.
Yeah, so he has he has the wind just blows right over it. For me, I'm often doing something that's got trellises or something like that, and so using a 2% is totally reasonable for something like that.
And it's just friction, right?
Yeah, essentially it's just kind of, as the wind blows around it, along it, it's still gathering up some of the load. So this is why in Toronto, I don't mind being somewhat conservative with my wind load. For Dave, doing something like a canopy in Bermuda might be less, might be more kind of refined about his wind load, because his wind load's going to govern. But for me, the majority of the time, the snow load is governing. Our snow load, we talked about in structures 1, that accumulated snow load wasn't something we were going to worry about, because that happened locally around curbs or parapets, around mechanical units, or on a low structure next to a high structure. Often our canopies are exactly that, and the snow load on them, I thought of another great canopy to show.
What's that one?
NFX with DTAH. It's not built yet, but Dufferin Grove. These were all examples that I wanted to show you guys. But snow load becomes kind of a really governing factor. So you can see that we might have this be just a small canopy here, and if this is our snow load projection, we might be in this range here. Sometimes what I might do, depending on if the canopy comes out to here, you can see that the snow load decreases quite a bit, and it's worth doing chunks in incremental values of that snow load acting on my model. If I'm in a relatively tight zone right here, I might just use the maximum snow load and see what the design implications are. Because it's certainly not going to hurt it if we're, if we're talking 3.5 kPa, and instead of going 3.5 to 3.3 kPa, I'm just using the 3.5 kPa over the whole surface. We're talking about a very nominal kind of structural increase in this, and it's conservative.
I like to put this in perspective because snow, the range of weight of snow starts at about 1 kilonewton per meter cubed for light fluffy snow to 10 kilonewtons per meter cubed when it's compressed like ice at the bottom of a major pack. And
that would be an aquarium of water.
Yeah,
that would be water.
So we typically treat snow as 3 kilonewtons per meter cubed, but at 1 kilonewton per meter cubed, light fluffy snow when it just falls, we're designing canopies, like just a little canopy over the doorway on a building. We're designing it for 3 meters of snow. And that's what the building code requires of us. 3 meters of light fluffy snow, or a whole meter of dense packed snow. Really high loads.
It's really high loads, but we're talking about 1 in 50-year storms. And if anyone remembers the images from Buffalo in 2014, I think it was, when they got 6 feet of snow in a 24-hour period. Canopies, there were some buildings at the backs, because of the wind, were almost completely open. You could go out your back door, but your front, the wind was up past your kind of first floor window. So that's why the accumulation in a 1 in 50-year storm is so high. Practically, hopefully, you never see that much, but by code, we're required to design for it. But when owners say this is ridiculous, why is it so high? You can say, yeah, it's ridiculous, but you don't want to come out of your 1 in 50-year snowstorm to a collapsed canopy in front of your door. So here are just some quick diagrams of the common kind of layouts of canopies. Often we have the moment connected to the side of a building. That's a detail that gets resolved. So our deflection, this is a cantilever, instead of our normal building code deflections of L/240 and L/360, we would cut that requirement in half, only because it's a cantilever, so the shape of how it bends looks more like half of a full-length member. So we would use L/120 and L/180. For one that has a backspan, where maybe we have this connected to the building and this as a column here, the backspan would use the L/120 and the L/360, and a cantilever would use the cantilever requirements. Maybe we have kind of an outdoor pergola or freestanding canopy structure that has columns at each end. That would look more like our normal kind of assembly. So our serviceability requirements, very similar to what we're used to for buildings. I do want to point out that our importance factor changes for serviceability. It's not 1 for a regular importance building. For regular importance building, snow becomes 0.9 and wind becomes 0.75. So for serviceability, this is kind of like saying we're talking about a 1 in 30-year storm instead of a 1 in 50-year storm.
What is ISIS?
ISLS. I went to great trouble.
ISLS.
I went to great trouble to change the font so that it was recognizably an I.
Right.
So that's our importance factor for serviceability limit states. Yeah, I have to actually go through every time I write this and change the font, because the normal fonts, all the standard fonts that are disgusting, make an I look like an L.
Yeah.
Vibration? I can't really think of a vibration criteria for canopies unless maybe it was an accessible canopy, and then I'd probably use the same criteria as a footbridge, which we're going to talk about next week. Again, that would really probably be about making an owner understand kind of applications of it, but we'll not worry about it for canopies now. And if you were designing that kind, you'd probably be thinking about it more as a
I don't think in 30 years I'd ever checked vibration on a canopy. Like, it's conceivable because we have for art and things. If they're dynamically sensitive, you get vortex shedding, that you get these amplified wind effects. But so it's conceivable that it would be important for a canopy, but I have never ever checked.
So free body diagrams, I only showed a uniformly distributed load as the three cases, but you could imagine instead we could have a point load at the tip, we could have a point load at the middle of the backspan, we could have a point load at the middle here, we could have point loads right over supports depending on what worst case we were trying to look at. So these are relatively normal looking free body diagrams, so I'm not going to spend a lot of time on that. There is no common canopy assembly. There are the ones that we see the most, though, which would probably be glass, fabric, an assembly of steel and infill with hanger rods, and we're going to talk about that specifically because that's kind of a misnomer. It's a thing we get asked a lot by architects, and I want to address that. And then probably a concrete cantilevered canopy that is maybe also a balcony. So I'm going to go through some projects that I've done. Like I said, I could have made this. I might have actually. I did cut some out of this. So I'm going to update this slide for you guys because not all of these are actually being done. I cut this down a couple.
I'm going to get us more coffee while you're talking. So I'm going to adjust that slide, and I'll lower the. I will adjust this slide to show only the projects that I actually used. All of these are in the slideshow. Some of them are just images instead. So this is under construction now. I designed it when I was pregnant with Duncan, so early 2018. I haven't heard anything about it since. The project went on hold for a bit, and then they'll probably come back to me in a panic when they go to build the canopy. That's my guess. Or else the base building engineer, the architect might have just used me for concept design and then went to the base building engineer and said, this can be done, here is our proof of concept. And that will often happen sometimes in the early stages. They want a specialist that can go through with the base building engineers kind of busy designing the huge building, and they don't have time to focus on this little bit. So I'm not sure if this is going to come back for me or if the base building engineer is handling this canopy. So this is what the architect sent me, and they had lots of questions, and I purposely kept this image because it's a really great place to talk about some of the questions. They thought hard about these being attached to a concrete structure. They even built in plates into the concrete so that they could attach anywhere along its length some way to connect this canopy. So that was really good forethought. They wanted to know about these braces here. I'll show you another slide in in a second. They asked about this lateral member here. In the end, that's not something that was needed. So they're talking here about racking of the system, and they referred to it as the lateral system. In the end, for strength, these as thin plates wasn't enough. They needed to be a little bit more, and once they were that, it was able to work to solve the racking problem as well. So they were showing this quite minimally, and by the time it worked for strength, it actually ended up looking more minimal because this started to get pretty busy with other elements in it. By the time we were moment connecting these at the top and bottom, these struts weren't needed. And the one I really want to talk about is they say how to make this rod connection work.
And do you want to talk about this? I know this is a thing you like to really talk about.
Go ahead, you had an idea. Or, I mean, I can...
Just talking about wind, just kind of this whole thought about wind.
Oh, I see.
About why so many canopies in Toronto show these rods. And they can be doing something, and sometimes they're not doing anything at all.
Yeah. So the challenge we have with a system like this is that the loads reverse. So for sure, the snow load pushing down is the dominant load, and the rods are very effective in helping resist the snow load, but they don't do anything for us for uplift. So and the uplift condition is a very real condition. So under uplift, the rods are considered to go slack, and they don't do anything for you. So we've got a number of things we can do about it. What you'll often see is that the rod is actually replaced with a pipe or something that can carry compression. So now you've got a system that works in either compression or tension. So it works for both the downward snow load and the upward wind load.
But we're talking about probably, so instead of a 19 diameter rod for tension only, we're probably talking about 3-inch.
Yeah, that's
probably
what I was
a
thinking.
2.5, 3-inch HSS or round pipe. So visibly, what kind of just disappears from your eye starts to be really noticeable.
That's right. It's a particularly unsatisfying solution when we have to tell an architect they have to use a rod or a pipe instead of a rod. The other alternative we have is to have two different load paths. For uplift, we could make the canopy a cantilever. Because the uplift force is going to be quite a bit smaller, we cantilever the canopy out of the wall for uplift. And then in downward, we're still moment connected at the wall, but in downward loads, we have the additional support from the tension rod. One problem with the tension rod is if they do go slack, they vibrate, and they may even visibly go slack.
Yeah, they can look like they've bent a little bit. It's like kind of pushing on an elastic band. You'll start to see that deformation. It doesn't, well, if it's too much, it could actually damage it.
The other problem with it is that under uplift, we have dramatically less stiffness than under downward load. So as the canopy is vibrating, it vibrates from stiff to unstiff, and so it can actually thunk as the rod straightens.
And if this is connected to structure in the building, that can really cause disturbances inside the building. It can be really noticeable.
So what we do is we pre-stress those rods so that they stay taut in serviceability conditions. At limit state, we're not so concerned, but at least at the serviceability condition, the loads that it's likely to see and that are likely to disturb people, we make sure that it stays in tension. And we can do that because we have the canopy itself is moment connected to the building. So when we tension that rod, we're not just lifting against the weight of the canopy, we're lifting against the moment connection. One thing I have unsuccessfully tried to argue is that by making the canopy porous, we eliminate the uplift. And when we eliminate the uplift, now we don't have to worry about the fact that the rods are going to go slack. We only design for the downward load case. And the argument was, whereas a flat screen, when we have wind blowing on a flat screen and it's trying to get through all the penetrations, there's a lot of volume of air has to pass through the screen. And so a screen has to be extremely porous to have a meaningful reduction in load.
You don't start to get any reduction in load until it's 25% porous.
But with a canopy, you've got wind passing over the two surfaces, creating a differential air pressure between the two, and a relatively small opening will relieve the pressure because you're not trying to transfer a large volume of air. So I tried to use that to suggest that on a canopy the wind is moving laterally, not perpendicularly. You don't have to move a large volume of air. I was unsuccessful. So that's one of these little side anecdotes that is not a specific learning point. But
now I've done a few of these recently, and it was dependent on where the wind, like where the snow loads were, that at the kind of worst case conditions, which were the end conditions, because we use a higher wind load at the end conditions, the uplift force really governed. And once I needed to moment connect for those loads, the member needed to be the size it needed to be, and the architect said, we just want that visually, like we don't want to change our member sizes around the building. So I took that and reapplied it through the entire system, and once I had solved that, even in the spots that didn't have as high of an uplift force, now without the rod, and this is the problem, sometimes we go through the process. I had already designed it with the rod in tension, and you know, it was an iterative process because we have to figure out how much we tension it, but it's only being applied for the serviceability condition, so we need it not to be there for the upward strength condition, but to be down there, to be there for the downward strength condition with the applied tension force. So there's like 3 separate models, or you need non-linear modeling software to look after that. I was like, you know what? These members are bigger. I'm going to go back and just check it without the rods at all. And it worked. We didn't need the rods. So we were going to go through, you know, a $20,000 expense for something we didn't actually need anymore. So I was able to tell the architect, listen, if you want those visually, that's fine, but they're not structural. And they said, you know what, we want them visually. And they said, okay, that's fine, but now they're decorative. You can do whatever you want. They're not strength dependent at all. They're not serviceability dependent at all. They can purely be decorative. And this was for a building for a particular city, and the architect didn't like the idea of putting lipstick on a pig, but the building owner very much wanted those visually. So they ended up putting in fake decorative rods.
Brian McKay-Lyons makes a distinction between ornament and decoration. And he calls ornament is a thing that maybe you could live without, but is actually doing something for the building, even though you could possibly live without it, versus decoration, which is
purely just plopping it,
cliche, right?
Plopping it on.
There are 2 other strategies on this that I wanted to talk about. One is the condition where we have a hanger rod and an uplift rod. It's uncommon, but it's something that we can do, have a 2-rod system. And then the other one is ballast. Ballast is extremely effective. You know, we have uplift in the order of 1 kPa, just crudely. Patio stones weigh about 1 kPa. And so without doing, you know, it's obviously you wouldn't do that on a glass canopy, but on a conventional canopy, to actually put weight on it as ballast means that you don't have to have a moment connection at your building, and that moment connection at the building can be problematic. If you're connecting to, for example, an existing brick and beam loft building or something, you can't realistically moment connect. But to ballast your canopy is a possibility. Anytime you're doing a green roof, I mean, we do tons of green roofs. A green roof generally is heavy enough to resist the wind uplift. So you've got an automatically ballasted system, which makes these tension rods.
There are some clauses now in the Toronto wind uplift report and green roof report that you have to do, that you assume some amount of your green roof is being blown away by the same thing you're using it to resist the loads of.
Right. Yeah.
It's funny, that's exactly why I was able to make that change with that one I was just talking about, that project I was talking about. They originally had a gravel system on top of the roof. They made an architectural change to get rid of that ballast, so now my wind load governed more than it did, and once it governed more than it did, I didn't need those tension rods anymore. So we're only on slide 12 out of 85, and we're 35 minutes into what I was hoping was going to be the short lecture. Okay, so here's what the final structural model looked. I want to make sure, I'm going to add an image for a project for you guys. I know I'm in the middle of another project, but Dave just talked about doing renovations in a brick and beam loft building, trying to add a canopy. I'm doing a project right now that just went out for tender that has exactly that, a canopy in an existing building, and it is painfully difficult and so many unknowns because we don't actually know what we're connecting into until we actually start construction. We have existing drawings, but nothing quite matches what the existing drawings say. So we don't know what hidden surprises are there. For that one, when it was out for costing, they kept saying, this number seems really high for the canopy. And I kept saying, I don't think it's high enough because it could be this, but it could be twice this because we literally have no idea what we're getting into. But I'm not an expert on costing. I just know that where the surprises are going to be is right here. So, you know, there's a real worry that the owner is going to have to take on these extra burdens later on. So I'll try to add one slide of that at the end, and you'll see that one kind of added on. So this is kind of what we ended up with. There was a few different conditions for this, one with really tall columns and one with really short columns. And then where they had doorways, so you can imagine a doorway right here, we couldn't bring our column down, so I had to add a torsion element that connected into these columns. So this canopy here tries to go down, it's connected to something back here that tries to twist, so it's moment connected at the ends to transfer that moment into the adjacent columns. Here's what if you look at the diagram for snow load, so this is very much what that diagram I just showed you for accumulated snow loads. You can see that the base load is 1.12 kPa, and you can see it went up to 4.9 kPa. So 5 meters of snow stacked up on the top of this canopy. This one, I did break it down because there was still value in, that was such a high snow load, to do 5 kPa over the whole canopy actually seemed really punitive. So I varied it in kind of 4 segment panels as an applied load. You can see that there are 4 segment panels that I varied the load down in.
5 kPa, imagine 5 meters of snow.
So here's just a structural analysis kind of showing that red is what we would consider overstressed, or our factored load is greater than our reduced capacity. You can see all of these members work. Here are the reactions. So I only showed you, I hid the reactions for the X and Y direction just because it muddled up the drawing a little bit. What I want to show you guys is that what we're taking as the canopy tries to dip down, it's causing a moment on the column, and we're resolving that as a couple. These canopies are identical for the canopy. The only major variable is the length of the column they're connecting to. So this is a much bigger column, but look at these reactions. We vary from, let's not look at the end conditions, but we vary from kind of 3 to 18. But over here, we vary from like 2 to 5 kilonewtons. It's because this was our couple on the short canopy, and this was our couple on the long canopy. So we've extended our moment arm for our kind of resolution of our canopy. Comes with a downside that this is a column that's now taller, that we also have to worry about buckling now. So it helps us for wind, but harms us for our compressive load.
It's also a lot more flexible now too, isn't it?
Also a lot more flexible. So that's why I wanted to show you these 2 images. Interestingly enough, so this one looks like it's the worst at these spots here. It's because our deformed shape, our columns are so stiff. This one over here is slightly more uniform. It's hard to tell in this, but this one is about the same amount of deflection, but the entire canopy deflects closer to that. So instead of having these peak ones with much more deflection, all of these were more uniform in their deflection amount. So this would be really important in how they detail the glass connections. If we have one panel dropping down further, we can't have an extended piece of glass over the top of this because that piece of glass would try to break. What we would need is discrete pieces of paneling that are allowed to rotate relative to each other.
Do they understand that you've magnified the deflections?
I did that in Structures 1, but yes, these are scaled. So these are not true to life deflections. These, if you modeled them at a 1-to-1, it would be barely noticeable. I wanted to show you guys the impact of our wind dragging along the canopy. So you can see the values aren't high, they're very, very low, but the weak axes of those columns, it can really govern those. If you remember, the architect originally was just showing a thin plate, and I'll show you what we ended up with. You can see the taller one, way less stiff, really has much more deformation in it. And then wind in and out of plane. This one's really important because these columns are inside the building while the canopy is outside of the building envelope. So these deformations became really important. But you can see right here, we're still talking about very low deflections for these wind loads. This is just for the canopy. So this is wind dragging forward and backwards on the canopy here. So it looks, again, these are very exaggerated, but we're talking about less than a millimeter of deformation in this. Wind uplift. So here's our wind. The first one was snow, which was about 17 millimeters downward. Our wind uplift is 11 meters upwards. So you can see they're pretty close to each other. And once we had this working for our gravity loads and for our wind uplift, we could have added the cable, and I gave the architect a very preliminary option showing the two in comparison. And they said, you mean you can get rid of our cables? And I was like, yeah, we can get rid of the cables with this small modification. And they much preferred the small modification to the outriggers than adding that cable. The other question they had asked, if I just go back to that racking one, they had asked about applying a lateral element here. But to make it work, it needed to be moment connected. Just applying a pinned element in between them did nothing for racking for us. And the values were so low that when I did the analysis, you could see we had very small kind of out of plane movement of these columns with one small modification. So again, we needed the modification for compressive loads. We were worried about buckling because, again, they were showing just a thin plate. So instead we made a T. We made a T section. And once we needed that T section for gravity loads, it solved all of our racking problems as well. So these are just the kind of the preliminary feedback structural drawings. So they had a bunch of different canopy types. We didn't even get into Canopy 2 and Canopy 3 for this conversation. So here you can see what I gave them and kind of confirming this information. Here is what the structural drawings needed to be. Do I have the column? I don't have the column written up in this, but the column was also, oh yeah, okay, so here. So our column ended up, so these were the columns here, they ended up being a T section, and our, so it was 200 millimeters deep, and that plate's 19 millimeters, making this one 181. And then this could be just a plate, and it varied from 225 at the back, where a moment is the worst, down to 175 at the tip. So they were able to kind of really make that profile quite thin at the front end of the canopy. So another canopy project, this one with Williamson. This one they have a building that they're building where I'm not the base building engineer, and the owner is a contractor that has a relationship with an engineer. So they had a very kind of specific way that they're used to building. So we're dealing with some light gauge steel stud installation, some wood structure, and then a joist system that is really designed by a separate fabricator. So they are much more heavily involved in the design process. So what this is basically a steel plate canopy with upturns on the edges and the corners cut out to be kind of the gutters. This is tilted to drain to where they need it to be, but that meant none of our structural members could go all the way to the edges. We needed to allow water to run in between the members and then down to those gutters. The outline of the existing building above is right here, and the outline of the existing building below is right here. So underneath, it's a very large canopy, but above, only this portion here is the canopy. So we're able to connect to the floor structure of level 2 of the second floor structure right here. So this was not designed by me. You can see that I provided them with the loads that they need to check. They would have done a preliminary design assuming something, but they don't know, is this supposed to be moment connected here? Is it something that's going to have a backspan? So you can see all of this is our cantilever zone, and these are all backspan elements. So here were the loads used in the design. For this one, 3.2 kPa, it was worth just keeping the 3.2 kPa consistent over the entire design, because look at our wind load. Downward was 2 kPa and upward was 2 kPa. So varying this snow load had a small incremental difference that was going to add an increased kind of level of work, and it was a lot easier for the building department to just see this line that says inclusive of snow load, and they were like checking a box. So here's what the structural model ended up looking like. You can see that these are angles that are welded to the steel plate, except for out here where we needed at our tip some HSSs, because that tip is really where it wanted to dip down. So we added HSSs there. And then we have the upturns at the ends of the canopy that, you know, they're structural, but they're not doing a whole lot for us. They're kind of just, they're smoothing out the edge. They're almost more of a stiffness element, if you want. This whole canopy would work without them as well.
I think this is really clever, Shannon, and you can see it in this one as well. The your corner detail. You know, Shannon talked about the way you can add vectors. You can add rotation vectors the same way you would add translation vectors. And so the moment at the back of the diagonal beam coming out splits and goes in 2 orthogonal directions, which avoided having to do a very complicated moment connection through 2 elements that were crossing.
So these are the big existing elements that it was going to be really messy to do a connection right there, punching through an envelope. These were HSSs. That was going to really kind of, we were trying to limit, and in fact, this whole structure runs underneath the existing, or not the existing building, it will be an existing building by the time this is built. And these are going to have clips welded down with insulation gaps or thermal breaks to those clips. So these are inside the these big members are inside the envelope. Everything else is outside the envelope. So we didn't want a complicated moment connection at the intersection between inside environment and outside environment. So this pulled the complex connection out and kept it in our outside environment, meaning our interior connections could be kept to be quite simple. So you can see these big members are the ones that are doing the framing for the second floor. And you can see my structural elements. Again, this is modeling software. It's not about graphics. So you can see this shows it being tipped down. It's actually tilted up. Don't worry about that. Here is the structural analysis image. You can see here that this says it fails, that it's over the strength capacity, or it's our factored load is greater than our reduced capacity. But this is, if you look at this, when I go into that, I'm able to make the engineering judgment that it's not actually a failure in our overall system. It's modeled in there to kind of help with the stiffness out at the tip of this canopy. So even though it shows it's overstressed, it's not something that I'm concerned about.
Do the students understand that the hot colors mean higher stress?
So
or is there a scale?
There's a scale shown at
great.
the bottom here, and I talk about it in one of the other examples. Yeah. That red down here is the one that shows that it's not working. And I did the same process in the guard one, which somebody wasn't here for. You.
Nice.
So these are the plate stresses, and I just this is something we check, but my goal here is that I'm trying to keep these stresses. You know, remember our steel can be up to 350 MPa. This is plate steel. I usually do a quick check, and if all of my stresses are below, 100, 150 MPa, I stop right there. In fact, the stresses for this were so low that to show you anything graphically, I changed my scale to be 25 MPa. So, 1, 2, 3, 4, about a tenth of the actual capacity of steel, just to show you what kind of the stress profile looks like on it. So this is under snow. Our steel sees our worst stresses kind of right here and at these locations here.
So Shannon, if the stresses are so low, why is the plate so big?
That's a good question. For a lot of these things we're worried about when we weld, we can get oil canning. So having some thick steel is really nice. And I'm going to show you, do you know what I didn't include in the Sisters of St. Joseph one? Yeah. The one from above. I'm going to add that.
Yeah. Yeah, because that's not one of the published photos, right?
No, I took that inside from up above. Yeah. So it can prevent kind of this distortion of the steel. For serviceability, maybe if we're getting some ponding there, we don't want to see it. Those are the main reasons I do it.
Yeah,
another reason?
For sure. Yeah. No, that's it. And you're going to get oil canning anyway on a hot day when it expands. It turns into a bit of a lasagna noodle, but
the thicker it is, the less likely it is.
The
less likely that is to happen.
So my rule of thumb is 1 to 100 as a thickness to span ratio. So if you have stiffening elements every 600 millimeters, then it needs to be 6 millimeters thick.
Why don't I add that?
It is an utterly arbitrary rule of thumb that I made up myself, but now that I have it, I follow it rigorously.
I always joke about our kids that we have a very rigorous schedule that we choose to follow or not, depending on the day. So here are the reactions. You can see that it only looks like we have reactions back here. That's because what would normally be considered a reaction is actually a load that's being transferred into those major structural elements. So those had to go get pulled off by looking at what the forces were in these elements, where they connected to the base building elements, and that is what I provided to the base building engineer. Here's a deflection image. So here's the deflection of the canopy for snow. You can see that it's my serviceability snow criteria. So this is a 1 in 30 year snowstorm. We get 10 millimeters of movement out there, which probably seems like a lot, but that's a 1 in 30 year snowstorm. It would be hard to, it's out past the building where it's hard to get a line on something to read it relative to. It would be stacked full of snow, which also distorts your line of image of what you're comparing it to. So 10 millimeters would be really noticeable if it was just this perfect, clean, crisp building, but stack that snow up on it and it starts to be a lot harder to see that deflection that's causing no permanent damage to anything at all. Here's our wind deflection, which for a 1 in 30-year storm, because it's our serviceability requirement, is 5 millimeters. So Sisters of St. Joseph, another plate steel canopy. So this one, they wanted this to look like the thinnest profile of steel imaginable out here at the end. We have a thicker system right here. This picture almost doesn't do it justice of just how gigantic this canopy is. And I'll show you in the structural drawings that it's almost astounding when you see how large it is. The length of this canopy is huge with, take a look, no backspan and not connected in any visible way to the base building. If you look in close right here, there is a backspan. For a gigantic canopy, we have this teeny tiny little backspan resolved as a couple going into these kind of classic Shim Sutcliffe concrete columns, really beautifully formed. We call them the peanut columns. I don't think they like it when we call them the peanut columns. So maybe if any of you go work for them, don't refer to the peanut columns. But these ended up having cast steel members into the columns. So here was my structural model. You can see that, so these modeling softwares often model things as one element. I needed to model the stiffness of that concrete column, but normally it would be just a line, but I also needed it to be my couple. So what I did was, acknowledging that concrete is this overall shape with steel in it, with ties that are dealing with shear, which we often can represent as diagonal members, as you guys remember in our trusses. That's the equivalent of our shear in an element, and top and bottom chords. So I modeled that concrete element, which wasn't part of my design. I was giving that back to the base building engineer, which happened to be one of Dave's employees. Did I actually work for you when I did this?
No.
Yes. Yes, I was still at Blackwell when I did this. It just wasn't my project at all. They just asked me to model the canopy because it was kind of my specialty. Yeah, it was 2010. Yeah. So I modeled this column as a truss, as a placeholder, and then was able to pull out these forces right here and say to the base building team in the office, here are your discrete forces that you need to make sure you design this column for. So this really just shows you the scale of this canopy, just how absolutely impressive it is in its size.
It's 4 or 5 meters, right?
Yeah. This is less impressive. This is where the modeling software really starts to break down. What we had here was actually 2 plates of steel with some things embedded in it. And then out here, the modeling software doesn't like that things are on 2 different planes. And also we have elements that taper and change profile, and the modeling software isn't great with handling that. It handles it great mathematically for determining the internal loads in the element. I mean, I could do this by hand and do that method of sections because it's not a normal loading diagram from the different standards that I've shown you. So I would have had to do method of sections, you know, at like 10 discrete points along its length with changing shape properties along its length to resist those loads. But the modeling software does all of that in absolute seconds. So you can see that it looks like absolute crap this way, but this isn't what we're using this software for. Here are the structural drawings. This was back when we still didn't even keep PDFs of our drawings. So I had to go in, hunt for these drawings, unlock them, and then do screen captures of the structural drawings. So you can see that we had members that split and broke within this kind of hidden shell of the deeper elements. Here are the loads that we used on the element. So you can see that there was top plate and bottom plate weights and our snow loads. This building was out far enough. You can see here's the accumulated snow load on the lower piece that was in between the two. So we only had accumulated snow load left back here, and this actually wasn't governed by accumulated snow load. You saw for that other project that it was 5 kPa. Now there's a few reasons there. That was next to a high-rise building and a very small canopy. This is against a relatively low building, and this is at the 2nd floor of the building, so that determines, that's part of the calculation for how much snow load falls down on it. This is also from an older code. So this was based on not even the 2010 building code, but the 2005 building code, which was OBC 2006. So 5 for the national and 2006 for the provincial, which had kind of much more lax accumulated snow load criteria. And I think some of that is part that we're seeing kind of increases in snow loads due to climatic changes, that we're getting these kind of surprising snow loads. So this was just before, like between those two codes, we had 1 in 50-year snowstorms 3 times. So we've been seeing how they change, and didn't have a big impact on kind of the main snow loads, but what they were really seeing was it impacted the accumulated snow load values. So as much as Dave is like, it's ridiculous, it's also not ridiculous simultaneously. I'm
not saying it's wrong. It's just big.
Yeah, it's big, but it's so big that it is almost ridiculous, but it is conceivable. I remember when we were in BC and we went skiing in Nelson, and there was snow piled on top of a little sign structure that was...
Let's get that image in here.
Yeah, I'll go see if I can find it. Snow load. That would be a good one to put on in all of my lectures. Awesome. So here's just some details so you can kind of see what these look like. We ended up with out at the low profile steel angles back to back with plate welded to it, and then these began to taper, and that note was on the structural drawings, but this was at the intersection. Here it was a bigger built up section, and then at the very back where we had our main structural members that were acting in torsion, those were HSS elements. Here is the strength analysis. Here is stress in the plate. Again, I'm just showing it at 50 kPa. This is, when we're talking about plate like this, and I didn't mention it with the last one, we can end up with local buckling being what governs. And part of the way they make you treat that analysis is they make you look at how overstressed it is, or what the stresses are on it, and they give you a formula for how to reduce the capacity of that stress based on the properties, the kind of the thickness to length ratio, the flat width ratio, and you have to reduce the strength accordingly. Even though the strength of the steel actually hasn't changed, they compensate by the fact that we're talking about local buckling by actually reducing the strength. So rather than do a rigorous buckling calculation, they just say, here's the quick way to do it, reduce the capacity by this amount. And so for this, I actually looked at each discrete element, what that and so instead of being 350, actually this was back when we still used 300 for plate and angles, instead of being 300 MPa, I think in spots I had to reduce it down to 200 and something, 230, so still quite high. Again, I didn't show what the maximums were. I changed the scale to 50, just so you could actually see that it's not that stressed for what it's doing. Here's a deflection diagram for full snow. You can see that out here at the tip, 40 millimeters. Far exceeds anything that you would consider standard criteria for snow load. Now, this has no finishes. The steel is the steel. It is strong enough, so there's no danger of yielding, which means if it deflects down to that 40 millimeters, when that snow comes off, it's going to go back to its original shape. We have not gone past the yielding stress of the steel this deflection is not associated with the yielding stress in any way, shape, or form. So it's in elastic zone. It's going to spring back to its original shape. So no permanent damage. So what we said to the client, or Shim Sutcliffe, who have very high design standards, we said, if you want it to be this profile, you will have to accept that in a 1 in 30-year storm, you will see this deflection. But I said, in a 1 in 10-year storm, you'd see this deflection, about 18 millimeters. But again, when that snow goes away, it leaves. And in a 1 in 10-year storm, you've still got a stack of snow up on it. There's nothing flat with it to read that with. There's no life safety. There's no damages to finishes. But we made that explicit to the client, and everyone accepted that as an okay solution to maintain that design idea.
It's a really important point that you just made, that if you have a straight canopy that is parallel to the building, then your eye can pick up things where things are no longer parallel, and that becomes apparent to you. You can really read the deflection. Where you've got a curvilinear shape around the perimeter like this could deflect 200 millimeters, and your eye would not.
It would be so hard to tell.
You wouldn't be able to see it.
So I'm going to add one more slide into this, and this is the image from above, where I was inside the building looking down at the top of the canopy. The fabricator was very careful to do all the welding on the top so that any kind of distortion of the member would be less visible from below. So we're welding this plate steel, so the visual implication is less from the bottom than it is from the top. But even still, the welding of it caused some distortion. And from the top, you could see a little bit of water standing in the locations. And I was with Howard Sutcliffe when I took that photo, and I was like, oh, I'm really sorry. We should have written maybe some criteria for heat progression and how to limit the possibility of oil canning due to welding. I didn't even think to add that into this, which you can do. It doesn't eliminate it, but it can give them some controls on it. Howard was like, you know what? It's a real thing. It rusts. You can see some water, it dries up pretty quick. He's like, I'm okay with it. So this architect who has these kind of really rigorous, very precise, Dave went to help them build their own cottage once, and didn't you guys take like a whole weekend to install like 20 screws or something? Like really beautiful and precise, and that is why they are some of the best in the world, but also very practical about real things. And so it was kind of, I was expecting this to be a horrible thing, and they were absolutely totally okay with it. So here is, you guys, some of you have probably walked through this, depending on where you live in the city, or if you're even in the city. Again, this is an old project that I had to go unlock the files, to the point that I would have had to go into XREFs and XREFs to eliminate the bubbles that show that these were site instructions or CCNs issued after, because the design of the canopy was kind of still ongoing when the main building was issued. So this is an old existing building, and this is a new building which is also attached to an old existing building that is off from the side here. So this is a heritage building with massive stone masonry walls that was built. So this building back here was built in 1918. I don't know when the original church was built, but well before the original parish hall, because the parish hall was built after the church. So this is much older. So we're connecting something large into this existing building. So we needed these connections to be doing the least amount of work they could possibly could. Masonry is fantastic in bearing. So we wanted this right here to just be some point loads sitting on masonry where we could embed some steel plates and have that problem go away. We needed all our work to really be happening with these steel columns, but the architect had the requirement that they wanted to see none of the connections. They wanted it to be perfectly hidden. But that means we needed all of the work to be happening inside the HSS. But this needed to be moment connections, kind of complex moment connections. So you can kind of see here a cross-section through the canopy that was sloped to drain. We had these HSS beams running at the top that had spider clips down to the glass. These were some of our connections into the existing masonry, where we put these clean kind of HSS bearing lintels that we could come in. We also needed to allow for tolerance for installation. You know, they're chipping out masonry to install this, and they want it to be perfect. So we had to build in something that allowed for tolerance in installation.
Well, and they didn't want a big escutcheon plate.
Yeah, they
right?
didn't want, like, one of the easy things to do is kind of clip something on the outside, but they didn't want to see that. They wanted it hidden as much as possible.
That's right. They didn't want the connection to have a profile any larger than the actual member that was being connected, and so we did this kind of reducer into a smaller pocket so that the brick would be clean around it.
And then this is the detail that we did for that moment connection of the beam to the column, where the entire thing happens internally. We had originally put this as a kind of a loose concept drawing on the drawings, and the fabricator's engineer came back and said, not possible, you can't build this, not possible. So we ended up, to kind of preserve the idea, took on the design of the connection. That wouldn't normally be our scope. It would be the fabricator's scope to design that connection. We put the forces on it. Instead, we took ownership of that connection and kind of walked them through the process on how they would build it and then install it in the field. And then over here on one side, they needed that not to have, this is the kind of the entranceway into the main building. They needed it not to have water run down there. So we needed to create a connection that didn't pick up the glass, but allowed water not to pour down there. So here was the model for the system. So these are our complex moment connections. These are our roller connections into our existing church, and here are our connections at the base. These were also moment connections. So the only places we had connections were roller connections here, and then moment connections at the base. Large HSSs, but spanning quite a far distance. Here's the structural analysis, which is clearly not doing much work. Everything is in that very light blue, which means it's at less than 50% of its capacity, or our factored loads are about half of what the reduced, or less, at least less than half of the reduced capacity. So why would I put such heavy elements on this if we didn't need it? It's because it was all governed by deflection. We're picking up glass plates. When I went back and looked at this, I was kind of like, oh, I feel like maybe I would have done an even tighter deflection requirement because it's glass. But this was about talking through exactly where the glass seams were going to be to allow that deflection, and the fabricator of the glass was okay with the deflection.
Now, just to be clear, I mean, glass can tolerate an awful lot of movement out of plane. So glass is thin, and it can bend.
Our guard deflection, 40 millimeters, is what's allowable for a guard that's only a meter tall.
Yeah, and a typical curtain wall deflection is L over 180. You know, so it can tolerate quite a bit of movement out of plane. It's in plane racking that's a real challenge for glass. Yep. Gotta go.
If you can get him set up over there and then come back.
Talk about, sorry, I'm going to run, but talk about the lateral drift under gravity loads because of the asymmetry of the frame. Yeah.
That's really, I'm going to not talk about it in this one. I have the one blower canopy. The deflection, you can see here's the deflection diagram. I actually did the calculation to show you that the member, the worst case deflection was 11 millimeters. And this thing is a nice flat thing. where you would really read that. And we actually talked about even a tighter deflection criteria, and we worked through this with the architect. Our actual deflection limit, we're 11 meters long. Our actual deflection was 31 millimeters. Our deflection limit was 31 millimeters, and our actual deflection was 29 millimeters. So you can see that this was designed to meet that L/360, or finishes that are susceptible to damage. We might have been able to loosen that up, but that L/180 is for kind of a much. You don't read that wall the same way you do that flat canopy. There was kind of this perception that we would really notice it relative to the two ends. So we kind of just decided to follow the L/360 criteria. The architect had no problem with those sizes. Had there been pushback with the architect on the sizes we were using, we might have said, okay, you know what, let's relax these deflection criteria and see if there's a change we can make. Here is actually some of the connection details. So here's the moment connection into the ground. Here is that finalized, beautiful moment connection. Here are the clips that come down that are going to pick up the spider clips for the glass. And here is our detail where we pocket into our existing brick. So they had to open it a bit bigger, fill any of these cores if they weren't already filled, all of these holes and bits with grout as much as they could. And then there's the tiny HSS that will be visible in the end, but you can see only nominally. And then they've kept all the brick because they kind of pulled it up very carefully, and then they'll pack it in and restore this as best they can. Here are the spider clips starting to be installed. And then here are some images of the finished canopy with the steel painted. So it was hard to see in those images, but that is just a gloriously long span for that glass canopy. You can see it here as well, just kind of this fantastically long canopy. So one blower. There are no existing pictures of it. I know the guy that fabricated it, installed it, actually took some pictures of it, but he is currently living on a boat he built somewhere near the equator, so I haven't been able to get the images from him, but there are no published images. There's just this rendering that exists. Everything else is just the drawings. So this is a steel structure that then was clad in with these ridiculously tiny, slender columns, then clad in a steel skin, and then had laminated to it this thin steel, stainless steel that was polished to a ridiculously high shine. And it actually does look like a mirror. And there's an image I'm going to show you later on that shows that. So you can see that originally this had 3 small openings and only a scattering of very, very slender columns. Here is the filigree of structure that's happening within that system. So it was 48 millimeter stainless steel top or 4.8 millimeter stainless steel top and bottom. So that is a very, very thin skin. That was going to be prone to local buckling and oil canning. So we added angles to stiffen that. And then we had elements along the major lines. And then these were fabricated in panels because this is on the 7th floor of the one bloor building. So these were fabricated in discrete sections. And so they needed to be able to be formed to have the openings. This was a first or various iterations where the opening sizes changed, where they then fabricated these and installed them piecemeal. Here's what we ended up with. So these were kind of the original drawings. We did lots of iterations where they changed to one big opening here. And then after this was already designed and fabrication had begun, they decided they wanted to infill these openings. So I had to go back and check and see if we met all of the criteria for that. These two little stubs were for, I believe, lighting of some sort. And they were heavy lights, so we wanted to check for kind of bending on this column. And it was probably applied to all of them, but I just needed to check one to see how it worked. When we have such slender columns like this, there's the opportunity for fabrication error. Nothing is going to be perfectly plumb. We're talking about small deflection or tolerance problems. If you guys remember back in Structures 1, and even as the refresher at the beginning of this, we talked about stability in a P delta effect, where if something moves out of plumb, that load is now eccentric from where it was supposed to be, which makes it want to push out even more. And then we check it again and see if it wants to push out even more. If each time we check it, that deformation gets smaller and smaller and smaller, we know that it'll start to move and then finally stop, even with that full load on it. If that deflection starts to get bigger and bigger and bigger, we know that applying that load would start to just make the building tip over. And that's something we call the P delta effect. And for this structure, P delta was a big issue. It is exactly what we needed to look at. We had wind as a drag and projection on the columns. We had wind gravity and upwards. We had dead loads and snow loads. This wasn't close enough to the rest of the high-rise that we didn't have to worry about accumulated snow loads. Here is the reactions at the base of my elements. You can see they're moment connected. We've got gravity loads of, in the 20 to 30 kilonewtons range. We've got moment connections in all directions. So we've got moment kind of around the base, we've got moment about X and moment about Y. So those were detailed with plates anchored into the existing concrete building. And then here's the deflection profile for dead and snow. I forgot to pull off what the actual deflection was, but we were well within tolerance. Here is our deformation for X. You can see that we start to move sideways quite a bit, but these again are to an amplified scale. So this amount was only 2 or 3 millimeters. Here it is in the Y direction. And here is an image from underneath looking up at the building. This is the ground below. That is how polished and shiny this building is, that this is the reflection of the ground below. The person who took this picture got themselves perfectly in the middle. In fact, you can see the detail at the base of the column right there. So here are just some quick images of canopies. Again, I wanted to keep these lectures kind of relatively short. They'll start to probably get quicker because kind of some of the things we've talked about will already be covered, and we can say, hey, remember that thing? We already talked about it. That's what's happening here. So a lot of these are ones Dave or I have worked on, but some of them are not. I just wanted to find some ones on the internet. If I could find who did them, I included that in the scope. I wanted to show you just a concrete canopy. That tussock moth he touched the other day had him up all night long, itching, and he's now still saying his finger hurts. So here's a concrete canopy. We did not do this, but you can see that it's got a connection back here, it's got a connection here, and it's got a connection here. And they've actually reduced some of the loading and self-weight in this spot right here. I might have, if I was designing this, might have suggested that they could probably have tapered this down to a finer edge out here had they wanted, or tapered the bottom sides to kind of give that read of a much thinner profile. Because out here, it's doing the least amount of work, so you could really lighten up that profile, and then also carrying less dead load. Another kind of concrete canopy over kind of an outdoor room. You can see that they really took the fact that concrete can be formed into any shape into serious consideration. This looks like it's a concrete canopy. I did this for Drew Mandel, where the building has absolutely amazing things happening on it. The little gem is the carport. We had to connect into these two back walls, this right here, we had to come out to this tip right here. We weren't using concrete, so steel, engineers tend to get into their head this kind of rigorous linear system where they would have put a beam here and a beam here and maybe cantilevered a series of things out here. But what I did was I took a member from here to here in a simple span, and then I cantilevered out something this way to pick up this corner, and then I cantilevered out from this point here as a simple span to my crossing member, and then cantilevered out to this tip right here. I might even add that plan. If I can find it, I would have to maybe go unlock that and get access to Blackwell's files for that, because I did this a long time ago. Plan Ave Road. I might not be able to get that in there for today in the time to upload this. What I like about this is a canopy for the Brickworks project, that here is an old canopy on the building, and here is a new canopy on the building. You can see the very industrial style construction, but that's reading off of some of the industrial looks of these buildings that were kind of very meant to have that imagery about them. A small glass canopy. This is at Fort York, the old Reno. You always have some funny little, you had a funny little story about this canopy, I thought. No? No. Well, here's an interesting thing. See this shadow line here? These didn't work for wind drag on it, or it didn't work enough to satisfy everyone on its movement. Because glass, as much as it can be loose in deflection in that direction, it's not as great in plane. It's so stiff that if the things that it's connected to aren't that stiff but strong, you can end up failing the glass. So this needed to be stiffened in the plane of the glass. So you can see these rods or cables would have been tightened to resist that tendency to rack under wind loads. This was in one of Dave's old lectures that I found. I don't think he did it. I don't even know what the project is, but you can see that this is more of a shade system. You can see snow on the ground, but nothing up here on the system. Each of these would have been designed to accumulate snow, and if it is, you know, 1.5 inches wide, I'd probably double its or triple its width in the amount of snow width that it could accumulate, as well as the height of snow that it could accumulate. So you can imagine if this is the element, you can get a blob of snow sitting on top of it. Kind of an outdoor canopy structure. This one, it looks like the columns, this has simple span elements everywhere. I'm not sure what the, okay, so these were moment frames. You can see that these were moment frames, but in spite of that, they were able to really refine the connection there at the tip. And again, the loads on this would be relatively nominal. It's picking up snow loads and wind loads, but not everywhere. So this is a spot where reducing the wind and the snow would be really a valuable engineering exercise, because you'd be able to really refine those elements. This, as much as it is a building, is a canopy. So there was a building down here and a building down here at this end as well, but you can probably consider this a canopy because it had wind coming underneath and wind at the top. When working on this, I certainly didn't think of it as a canopy. I mean, I did for calculating the wind loads. And in fact, this was so complex that RWDI did a wind study and snow study on this project. And you guys remember when I talked about loading combination? Did he just say that?
I'll be right back.
Oh, he didn't say it again. They're cranky when they wake up. I'm glad it's his morning to deal with it. What was I saying? Oh yeah, RWDI did the wind analysis and snow analysis on this building, and I ended up with 1,200 load cases because of that. Here is that classic system where we have the tension cables. You can see that they have big plates connecting into the existing brick masonry, and these are cables with elements that allow them to tension it. So these couplers allow them to actually tension that cable, so they've probably actually gotten it to work so that they'd be unloading the cables in wind load. I can't remember what the name of this building is. So this is a project, and this is Dave's story, so I feel a little bad telling it. The top of this would be designed as a canopy, or I would think of it as a canopy. You know, it's got wind on both sides. These were cantilevered up columns. MJMA, who we've worked with forever, said they wanted these to be as small as possible. So Dave did the analysis and he said, okay, they need to be this big. I said, no, that's too big. And he said, okay, well, what if we kind of went through and made them rectangles and put a plate on it? And I said, no, still too big, because we could get a thicker wall section. He said, okay, well, what if we did an ellipse so you'd only see the thickness in one direction? And I said, no, it's still too big. So Dave kind of was like, what if we made them solid steel? And they went, yes, make that happen. So it got put on the structural drawings, and no one really thought much of it. And then all of a sudden, it came time to be built. It was clear on the drawings, but the contractor was like, are you serious? Are you kidding? Do you really need this to be solid? And everyone was like, yep, has to be solid. This guy was like, I don't even know where to get that. He sourced, it was tank axles somewhere in like Kentucky, and had them shipped to the site. And one of the contractors wasn't thinking about it and kind of went to kick it on site, and ended up like seriously damaging themselves.
I think he actually tried to pick it up with a forklift, and instead of lifting it, the forklift tipped. It was too heavy to lift with the forklift.
I just wanted...
We had a story on Jackson Triggs Winery. We had a similar thing like that, where we were using 3-inch thick plates, and the contractor, he just assumed it was like a chocolate Easter bunny, and it was hollow, made out of thin plate, and was surprised that they couldn't lift them.
So I just wanted to show you some glass canopies, like detailing where the glass goes around the column and some of the spider clips. We're going to do a whole kind of module on glass, so I just wanted to show you how it works in canopies, or some common glass canopies. This is the City Hall canopy. We did this. You did this, right?
Square,
Nathan Phillips Square. I had no part of it. Do you have any anecdotes about this? I don't...
Yeah, I think it's
that it took a long time to build, and we all thought it was canceled forever. Like, this project was on our books for like 8 years or something. And then one day we just got a call saying, yeah, so we're building it. And everyone was like, what? I think we stored the files. Like, I think we actually like marked it as checked, not ever happening, and like stored the files. And this was like way back when, where you physically didn't have digital files. You stored your paper files off site.
This one I find really interesting because of the load paths. In the direction, I want to point to things, but of course that doesn't help you.
Yes, it does.
Oh, I see. Okay, so let me in this direction, when the wind is blowing parallel to that axis, these two elements cantilever up, and they're joined together at the base, and that's what provides the base fixity, or the majority of the base fixity comes from being joined together, and so they cantilever up. In this direction, they don't cantilever up. We don't have base fixity here. In this direction, it's a very traditional moment resisting steel frame. So you can see you get your fixity from this big beam element at the top. And then in the end, of course, architecturally, the effect is one big long ribbon, right? It's one continuous member. But I thought that was really a clever solution to have the two different systems.
One of the other things is that the roof is essentially similar to a two-way slab. You know, it's a 3D truss. I'm inferring that this is a two-way...
triadetic space frame.
So triadetic space frame, which means it is working in all directions, which is very similar to what our two-way concrete slab is. Mm-hmm. This would stop working if the proportions were changed too much, but you can see it's pretty darn close to square, which kind of gives it that ability to work that way. This is a fun one that I did. That's they're still just finishing up the site work. You know, this was a building, a condo in kind of Mississauga way. It might still be in the Toronto side, but it's pretty darn close to the border. And this has a series of really fantastic outdoor elements on this park that they've provided. There's like a little amphitheater, there's some fancy stairs, there's terraced bleacher seating, there's a boardwalk, a little bridge. But this was really cool. The architect found an image of a project by Jablonski. No.
Kieran Timberlake.
Who's the California architecture firm that does fancy houses? That we did a bunch of their houses, and we met the guy, the guy at the Wood Awards.
Oh my God.
CW.
When it occurs to us, we will share.
Anyway, the architect I was working with saw an image of their thing, and they said, we want to build that. I'm like, you want it to look similar? They're like, no, we want to build that. I had to tell them that it was, you know, they had some different loading conditions than we would have, and that we had no images of how the detailing worked. And they had some things that we couldn't see what was happening at the top. But I said, all right, I'll do my best. Let's make this work. So all of these connections are actually, the way they built it actually ends up being less, it's more clunky than what I had detailed. I had originally detailed something that was much more refined than even this, but the fabricator, this was maybe kind of one of the most ambitious things they had done, and they proposed to do this, and the architect agreed to kind of lower the bar for that connection. So these are a series of custom aluminum mullions connected to steel HSSs that are, the columns are cantilevered up for wind load, making these, actually, let's go on to the, I don't have the next models. I can't remember. I think in one direction it's a moment frame, and in one direction they're cantilevered. Yeah, so in this direction, they're moment frames, where we only have 2 columns in that direction. And in this direction, the columns themselves are cantilevered up because we have a series of 5 of them that can do the work. So the only thing going in that long direction are these aluminum mullions that are providing no fixity for the overall system. So essentially we have a series of 5 individual frames acting independently that needed to be stiff enough that if they acted independently too much, they could cause damage to those kind of aluminum mullions.
This is a good example where the projected profile is very thin, so it would pick up very little wind, and so you would design for friction on the surface, right?
I wanted to be really conservative with this because, you know, it was kind of a unique thin structure that I did projection. I looked at projection and I looked at drag, and I compared the two, and depending on what direction it was, one used one and one used the other. Because in, and what I did was actually for the top elements, I used projection in that direction and drag on these. And in that direction, I used projection on the front surface and drag along the rest of the surface. So kind of this is where engineering judgment really came into play. Like, how much did I think was reasonable? Because I didn't want to penalize the project, but I wanted to make sure I satisfied the building code and the building department, and myself as an engineer, that I had done something rigorous and responsible. And this is where the onus is: did you do something that another reasonable, or a selection of practicing engineers might have done? And so I also needed to be able to say, would I satisfy another engineer who came and looked at this?
The base detail is really lovely. So what we would normally see at column bases is you'd have a pier that sticks up roughly 200 millimeters, would be bigger than your base plate. Your base plate would be roughly 150 millimeters smaller, and then your column 150 millimeters smaller than that. So you know, the normal condition is quite a large concrete pier with exposed anchor bolts, but you've managed to get something really, really elegant and minimal.
That's a cover plate. The real connection is happening down below grade. I allowed them to keep the top of their concrete below grade and set their pier, the pier down. So the base plate was designed to take into the fact that it could be in a rusting condition, so it was oversized. They had to protect the elements, and then they filled that zone with free draining material, so it wouldn't be something that would clump. Like, we didn't just put dirt there, we kept free draining elements around it so that if water did get there, it would have the tendency to drain away. And then they put their finishes on top, and then they put a cover plate, more just to hide the rough edges of the brick.
Sure. And the cover plate, is it two pieces, or was it something, a single piece and you lift it up?
That wasn't even my scope. I'm guessing that they had it loose and came in and kind of just touch welded it, and then painted it up to stop water from kind of ponding on that. I just showed the detail going down, and that was the architect added that.
And you say you oversized the base to vary it. How much? Like, did you? Was that?
I just made it.
Up
I just made it thicker. I didn't make it bigger that way, because rust. Really, when you see rust kind of come off of things, it expands to 10 times its size. So one millimeter of rust is only 1/10 of a millimeter of the steel that's disappeared. And then the rust itself, if it can't be disturbed, actually becomes the protective coating for the steel below, which is really exactly the principle behind Corten steel. So if, you know, a 13 millimeter plate worked, I made it a 19 millimeter plate just for my own satisfaction.
And the other thing I wanted to ask, what was your lateral drift criteria? Because your columns are really nice and slender.
I looked at H/500.
Really?
Yep. So I looked at the base building criteria of H/500. I can't remember who met it. We might have been over that, but we have no finishes that can be damaged. So most of that is about satisfying windows within your frames, that you don't want to crush or damage your windows or have them pop out of the shoes that they're in and fall out onto the ground. We had none of that. I might have relaxed the criteria.
I'm using as much as...
I you know what, now that I'm thinking about it, I think it might have been L/180 or even L/90, but...
L/90, yeah, I was going to say, I'm using 1%
because
as my drift
they're
criteria.
cantilevering up. But I remember going through this one, and deflection was surprisingly not an issue.
Because the projected area is so small.
The projected area is so small, and I had moment frames in this direction and 5 cantilevers, or 10 cantilevers in that direction, that the loads were so nominal. And even then, my loads were made up and quite high. So I you know, an alternative is that I use H/500, but a low importance category. Actually, that doesn't change the deflection criteria, so that wouldn't have changed the applied load. 0.75 for wind is 0.75 for all of the importance categories.
What a handsome canopy that is.
Designed and created by him. There was no architect, was there?
There was a landscape architect, but they really had no input on this.
So just to be clear, this is somewhat literal, but it's at a sailing club park. Like, you can see that this is where there's literally a sailboat in the background.
That's right. Our mandate was make something that give us a structure that fits in the context of a marina. So it had to look marine-like. So some of these things are very easy. As soon as you use fabric, it evokes the sails. White painted steel is very marine-like. All the turnbuckles and hardware and stainless steel and things. So this particular canopy was a sculptural form. So the form was not derived from program, except they did anticipate having performances. Do we have multiple images, or is this the image?
No, one image.
So they did anticipate having performances. So making it into two membranes was a formal idea. It was just about architectural expression. It didn't need to provide shelter other than nominal shelter. So having a gap here wasn't particularly a problem between the two membranes. Back here, you can see the membrane slopes down. That element along here is a gutter. This membrane slopes down, and there's another gutter up here. Through the bottom, from the top gutter through the bottom gutter, are a series of stainless steel pre-stressed cables at a close spacing. They're maybe 150 millimeters apart. The idea is that in the winter, winter rain will run down here, collect in the gutter, run down the cable, and form an ice screen. They've also planted down here with the idea that the planting can grow up and create a screen which becomes the backdrop for performances. This membrane was originally conceived as essentially triangular, so that form. The client late in the day wanted additional coverage. So we floated a spar back here. You can't tell, but this necessarily, but this element back here isn't connected to the column. It just floats there and pushes out these 2 points, and is held in space by tension cables. A few other interesting details that there was a desire to articulate the top of the mast, so we did a little step down to a smaller size, and then up at the top. It offset and continued on at a smaller size. Membranes have extremely high forces in them.
Remember, we're doing a whole
Right.
lecture on fabric structures.
Okay,
don't
so
spend too much time on this because we're way over on this lecture.
Okay, so we'll talk about the canopy elements. Well, I think that's really it. We'll talk a lot about this.
And this one's going to come back into it. This one's a great precedent for that. The one thing that's really interesting about this project, and I honestly wasn't paying attention to you, so you might have addressed it, was the site conditions were kind of really difficult to work with. If it was concrete, they needed to get them in early, and they were expensive. No one was happy with the concrete foundation solution. It gave no leeway because they were still designing the upper portion of it when foundations needed to go in if it was concrete, because it was the season before, right, that they would have needed to do the foundation.
That's right, yeah.
So Dave proposed doing steel foundations, where this is all connected to basically a steel frame like you would see in a roof for racking below grade. So there's a filigree of steel beams, similar to what you do with concrete grade beams, below the soil, which is what all of this is connected into. And they were able to erect that in like a day or something.
The foundation
ridiculous.
went in a weekend.
It was absolutely wild.
So it's very quick, very lightweight compared to concrete, which is good because it was a fill site. One of the huge advantages is that all of the anchor bolts and all the lugs to receive the cables were all in exactly the right spot. Perfect. Because they were done by the steel fabricator who had to build the steel on top of it.
So he was able to kind of do a fit up in his shop for elements and know exactly where things were. And you've heard me say before that the number one thing that is wrong in a project is where those anchor bolts are. Yeah. They're probably wrong 60% of the time. So, you know, that's just something to build into your thought process when you're designing things. I just wanted to show a few more kind of fabric canopies. Again, we're going to be talking a lot about fabric canopies. Now, this is one Dave did. Again, we're going to talk about this in the fabric lecture, so I'm going to breeze through it because we've really pushed you guys over the 3 hours. But some of the other lectures later on, I think, will be shorter, and hopefully you guys find it somewhat interesting. And there's not a lot of work demand with this course, so you can pay for it by listening to us just a little bit longer.
So this is a fabric canopy in Bermuda. This is a flat membrane. So normally with fabric structures, you want a lot of shape in the membrane. That was inconsistent with the architectural intent. So these are perfectly flat membranes. They span just because they're so tight. It's a PTFE fabric, so fiberglass with Teflon, which makes it non-combustible, which is a big benefit. This canopy has been through several hurricanes now. In fact, just Teddy last week. Teddy last week had sustained winds of 140 miles an hour.
Miles an hour, what's that? Kilometers? 220, 230 kilometers an hour.
Yeah, so we talked about how crazy 5 kPa snow load is on some of the canopies Shannon was talking about. We see 5 kPa of wind load on this canopy. So just tremendous forces. But they've stood up admirably. The fabrics are extremely strong.
So there was another canopy on that site as well. What I love about this, I have an image somewhere of Dave. Our cottage is near where the fabricator is for this project, which is Northern Ontario, or like Southern Northern Ontario, and these were fabricated there and then shipped down to Bermuda. I have a picture of Dave standing on this canopy. I couldn't find that, but we did find a picture of this guy standing on the canopy instead.
Pretty sure that's Derek, the fabricator.
That is Derek, now that I look at it. You can tell by his scrawny, tall frame. So this is the guy that's disappeared somewhere. Not disappeared, him and his family have retired, and he's a concert cellist, a deep water welder, so a marine welder, like underground welder, best steel fabricator I've ever worked with. Yeah. What other weird things?
Basically, he's Buckaroo Banzai. Yeah, I'm sure he's a rock star as well.
He's good at absolutely everything. He's shown up at our cottage at like midnight with 30 beer, like just one of the most interesting guys you'll ever meet.
But what you can't see, unfortunately, because the beam is in the way, but his feet don't even make a divot in the
you would expect it like standing on a trampoline. You can see kind of where you're standing on it. He's doing absolutely nothing.
Yeah, the membrane is so tight and rigid, it's like walking on a wood floor.
Okay, so we've gone long. I'm really sorry. That's everything we wanted to talk about canopies. I'll add in those few slides, so you guys might see a few extra slides or slight modifications that aren't in this, but they're there for you to look at and kind of go forward thinking about these things. Feel free to email any questions. You can do it within Quercus, or you can email me directly, and I'll post any answers that you guys may have. There's probably not too heavy on the questions, I can't imagine, unless there was something kind of really unique or a specific thing you wanted to ask about, but I can't really see kind of the places for that in this. It's not like you're doing complex math or anything for this. So thanks for listening to us, and the next one is pedestrian bridges, fences, I believe, and light posts. So, you know, the pedestrian bridges, and then light posts and fences I'll probably do in one. And that one should be a quick one, some free body diagrams and kind of some typical things of what we're looking. What's wrong, buddy? You want to come see? Come here. Come here.
My big finger hurts, Daddy.
Say hi.
Come say hi. Come say hi to everyone. Hi. Can you blow all the students a kiss? Do you know what they learned about today? They learned about when things are stable.
Daddy.
Yeah. Okay. All right. Thanks, guys. Bye.